think here we go then. All right, well, first of all, I'd like to thank the organizers very much for having me. It's a pleasure to be speaking here today. I confess that my title's a little bit misleading in that I'm saying that I'm talking about ergodic theory. I'm talking about what is an ergodic theorem, but I'm not going to be talking about ergodic transformations to go with it. So I'm perhaps half-truthful in the title. Let me show you what I mean. Let me figure out how to work the... Hello? Hello, computer. Okay, so let's do this the nice old-fashioned way. So the central question has generally been to relate two sorts of regularity, one traditionally analytic and one, the algorithmic randomness notion we are here to celebrate. Random points, in some sense, they're regular with respect to measure. They don't have rare measure theoretic properties of the appropriate sort. And ergodic transformations say that for almost every point, the orbits of certain transformations will have regularity properties. And if that transformation is ergodic, it's a very strong regularity property. If it's not necessarily ergodic, there may still be some sort of regularity properties, but not as strong. So the question is, well, how can you relate these ideas? And I'm not going to belabor this. We're working in the Cantor space today. As Mathieu pointed out, or Jason, I think, it doesn't necessarily matter so much which one. And the standard topology that we normally use, the standard Lebesgue measure. But now let me start with the bit that has not been heavily discussed. I'm framing ergodic theory a little bit differently from the way Mathieu did. So let's just say that it's a way for describing how a system changes over time. And some of you may have seen something like this slide before. You have not seen this precise slide before I changed the type of gas we're talking about. So we have a neon atom in a box, and it is, at some point, X. And what we have is a force that operates on this atom, and after 1 second, this force has moved has moved the atom to position T of X, and you can see that if you iterate that n times, you get the position after n seconds. So what one generally looks at with an ergodic theorem is you look at the orbit of X under T, and you say, well, what is this atom doing over time? Maybe T doesn't move the atom at all. That's a very boring transformation. Maybe T takes the atom to the 8 corners of the box in turn. Maybe it does something else. Maybe it moves it more or less evenly throughout the box. But this is the sort of thing we're looking at here. So let's make this formal. Take your standard probability space. Take your transformation T, and we'll take some measurable subset of that. And we're going to work with some definitions here. So we'll start by talking about measure-preserving transformations. And to do that, you just say, well, take any measurable set. What does T map to that set? Well, it has to be a set of the same measure. So maybe not the same set, maybe it maps half the box to another half of the box, but the measure is preserved. We could talk about a set being T invariant if not only does it preserve the measure of that particular set, if it preserves the set itself up to a null set. And finally, we can say that T is ergodic if it's not only measure preserving, but the only T invariant measurable subsets have measure 0 or measure 1. So for instance, if it's ergodic, we're looking at this box as our set. It can't take, for instance, half of this box and map it only to itself, half of this box and map it only to itself. That would be measure preserving, but not ergodic. If it's going to be ergodic, it has to, if you have an invariant subset, it either has to be essentially the whole box or essentially none of it. It can't split it in half. So, the theorem I'm talking about today is Birkhoff's ergodic theorem. Here it is for the ergodic transformation. So you take a probability space, take your favorite ergodic map, take a nicely integrable function, and then for almost all of the points in that space, the limit of the average values of f on the first n iterates, take that limit, you're going to actually get the integral of f over the space. And the way we normally look at it, because, you know, recursion theorists at least tend to be more at home with sets than functions, is to consider the characteristic functions of particular measurable sets. So then this becomes saying that the limit of the amount of time, the iterates of t on x spend in A, that average is essentially the space average as well. So time average equals space average. But of course, if we're talking about randomness of particular points, we aren't going to talk about this general theorem. We need to talk about whether the theorem holds for a point. So let's talk about the points for which that particular theorem holds. Again, probability space. Here I'm only asking that t be measure preserving. And I'm going to take some collection of nicely integrable functions. And the first definition I'm going to make is one that's not normally made, a weak Birkhoff point. So I'm just saying that a point is a weak Birkhoff point for this transformation with respect to that collection of functions if for whatever function you take in your set f, that limit actually converges. You aren't asking that it converge to anything in particular, you're just hoping for convergence.
Is that what analysts call the
Is it? I couldn't answer that, I'm afraid.
It reminds me of.
Okay. Okay. So then we not only have a weak Birkhoff point, we have a Birkhoff point. If not only does it converge, it converges to what we would want it to converge to. And that last bit really only makes sense if you're dealing with an ergodic T. The top definition makes sense as well for anything that's simply measure preserving. So let's see, the idea of a Birkhoff point has been studied by very many people. Mathieu cited, I think, both of these results. I was having trouble fitting all of the names on the slide. But this has been gone over. If you ask the T be ergodic, you can characterize Martin-Luff randomness and Schnorr randomness that way. So a point is Martin-Luff random if it's the Birkhoff point for ergodic maps with respect to effectively closed sets. Or a point is Schnorr random if it's a Birkhoff point for ergodic maps with respect to effectively closed sets with computable measure. And somehow that distinction makes quite good sense. So then the next question that one could ask, can you characterize randomness in terms of being a weak Birkhoff point? So you don't need your transformations to be ergodic. And half of that answer was had for Martin-Luff randomness anyway. By 1997, Nguyen said that, well, if you have a Martin-Luff random element of the Cantor space, then essentially you have a weak Birkhoff point for the class of computable functions. So for any computable function f, any computable measure preserving transformation t, you can at least say that that limit exists. So that's half of it. And in the past few months, Henry Tausner and I proved the converse. We showed that if you have something that's not Martin-Luff random, then you can produce a computable function f and a computable measure preserving transformation t such that that limit doesn't exist. So now we actually have a full characterization of Martin-Löf randomness in terms of weak Birkhoff points. So let me just say a little bit about how that goes. I think I said the theorem at Dagstuhl and didn't really give much.
That's
Yep.
a weak Birkhoff.
Oh, yeah.
Where-
Well,
so
it's
the weak Birkhoff.
yeah.
What about Birkhoff?
Oh, that was done by, let's see, disturbingly many people, and if I try to get it now, I'm going to leave someone out.
Oh, all right.
So, yeah.
Well, I guess what I mean is, can you find an ergodic map where the limit doesn't exist?
No.
If X is not Martin-Löf random, can you find an ergodic? Yeah.
Wait.
Oh yeah, I guess
think-
that's what this
yeah.
says, right? Okay.
Yeah.
Um,
So ergodic, non-ergodic, also non-ergodic. And I'm going to say a little bit about this proof just because one of the key tools is going to be rather important for the next bit that I'm going to be talking about, this idea of upcrossings. And it's apparently a very standard tool in proving ergodic theorems. So, how do you start? You take your favorite measure-preserving invertible transformation t, you take some point in the space, you take a measurable function, and now the idea is that if you have two rationals, alpha and beta, alpha smaller, then you can form an upcrossing sequence for this alpha and beta, and it's just a sequence of natural numbers, an interwoven sequence of u's and v's, such that for any of the u's, the average of f on all of the values of the iterates of t up to that uth value, that average falls below alpha, and at any of the v's, the average of f of tj of x falls above beta. And then you can ask questions like, how long could one of these upcrossing sequences be? You know, you could ask, for say, I don't know, 1/4 and 1/2, how long a sequence can you get so that that average is below 1/4, then heads above 1/2, then falls below 1/4 again, above 1/2, so on and so forth. And of course, you can see how this can be used to define convergence, yeah? You just keep making alpha and beta closer together and keep asking about the soup of the lengths of the upcrossing sequences. And that's essentially what we did in the construction. I'm just going to say that, well, suppose x isn't Martin-Löf random, then it's in some Martin-Löf test, the intersection thereof. And what we did was we built a set A and a transformation T such that T mapped every element that ended up in that intersection through A half the time. And then we mapped it through another set B disjoint from A to bring its average time in A back down to 1/3. So keep mapping it through A, average goes up to 1/2, map it through something else for a very long time until that average falls back down. But formally what we're just saying is that when we saw a string sigma enter some vj and we used a very carefully chosen subcollection of the test components, but if you have a string sigma entering a vj, well, you just make sure that you have some sort of increase on the number of upcrossings. So you just make sure that it goes above 1/2 and then down below 1/3 again. You've added to the length of your upcrossing sequences for everything that could possibly be in the test at that point, every x extending that sigma. Okay. So that's how we used upcrossings in the first part of this. But then, of course, there's another question. This worked for computable, the set of computable f. What do we do if we're interested in lower semi-computable f instead? Well, we're probably going to end up with a stronger randomness notion compensating for the more general class of functions. But what do we want to do? Well, we'd like to show that a theorem of the form, if this is random in this way, then it must be a weak Birkhoff point for lower semi-computable functions. So that means we need to show that the limit exists. We want to bound the number of upcrossings in F. So you can tell by the fact that this isn't centered on the slide that something is coming up. Namely, we have a problem. And the problem is that all we have to approximate our lower semi-computable function, we have an increasing sequence, a uniformly computable increasing sequence of functions that converge to it. And if we work with one of those, we think we have an upcrossing sequence for one of those. Well, these functions are increasing. We could very well lose that upcrossing sequence when we look at our next approximation to F. So how do we handle this, since we really just have to work with those approximations? And our answer was to generalize the idea of an upcrossing sequence. So this slide is essentially identical to the last one other than the title. And the fact that here we don't have just a measurable function f, we're assuming we have a measurable function f and a measurable function h. And the definition is, for a loose upcrossing sequence, is very much the same as an upcrossing sequence, except that we aren't requiring that that f of tj of x, the average of that at the v points be above beta. That's a little bit stronger than we want right now. We're going to use f for the lower bound for alpha and f plus h for the upper bound. So maybe f doesn't have to get there on its own. It can have a little bit of help from h. And the idea here is that h is going to be a very, very small function.
But positive.
Yeah. If it's negative, this becomes a little bit less interesting. So now we can talk about a loose upcrossing sequence. We can talk about the supremum of the length of loose upcrossing sequences, just like we could for an upcrossing sequence. And we found out this was enough to get us a partial result. So the same sort of result that Union had in 1997. We said, well, if you have something that's weakly to random, then for any lower semi-computable function, you can have that limit. So just a reminder, weak to randomness is defined very similarly to Martin-Luft randomness, except that the measures of the test components don't have to go to 0 at a pre-specified rate. The 1/2 to the I condition doesn't hold necessarily. All you need is that their measures converge off to 0. You don't care how fast. So it's, yes, Andre discussed this in his talk. So now we have a stronger randomness notion, and we know this works. And how does this go? Well, proof by contrapositive. Suppose the limit doesn't converge. Then, pick some alpha and beta. You have an infinite upcrossing sequence. And then essentially what we did was we defined a generalized Martin-Luft test, the sort where the rate of convergence doesn't matter, that x would have to be contained in. And so how did we do it? We just looked at loose upcrossing sequences where the second function was a difference between two approximations. So say Vn would be defined as the set of all x where you could keep searching past n for some new set, some new approximation m, where you could find at least n loose upcrossing sequences where the functions involved are the nth approximation, and then the difference between that approximation and the mth. So then they're nested. That works out well. And I feel a little bit bad hiding all of the fun stuff in the last bullet point, technical lemma. And that's because I have 30 minutes instead of, say, 2 hours. But it's just not a very long proof. You, all of the work, well, it's not a very long proof once you accept the technical lemma. But it's a nice way of just saying, okay, well, suppose the limit doesn't converge. Let's build ourselves a generalized Martin-Luft test that's going to contain the point we're interested in. But now the question that we have at this stage is this really going to be the right notion? So for instance, could you get a reversal here? And we're not sure that you can. In fact, we're a little bit skeptical that this is as well as you can do. Because to get the, in this proof, we end up using a very odd mishmash of ergodic theorems. We end up using, in our proof, sometimes we end up needing a constructive version, sometimes we end up using the non-constructive version. We can't help but feel that there's a much tighter proof out there that might give you a weaker notion of randomness that would still be enough. So, improvements. So now I can feel a little bit like, some theoretical computer scientists who say, suppose P equals NP, then you have this awesome theorem. This theorem is perhaps not quite so awesome as all that, but there's an analytic condition that, if it is true, would let us take it all the way to balanced random, which Andre also talked about. So a balanced test, well, you just have your sequence of RE tests, where the ith test is chosen by a 2n RE function, and the standard Martin-Luft measure condition holds. And that condition up there it seems very strong to us. We're hypothesizing that, well, suppose you have f, suppose you have a positive epsilon, suppose you have this nice sequence of functions whose L infinity norms are all rather small, below epsilon. Then we're saying that you could bound the integral over the space of the soups of the upcrossing soups by something that's computably bounded, well, not officially computable, but you could compute the bound from the L infinity norm of f and from epsilon. And if that all happens to be true, then we can weaken it to balanced random. It's strong. It's a very strong condition. We don't see a way to rule it out at this point. We've started talking to some people who actually do that sort of thing for a living. And we're hopeful that at some point we'll be able to figure out what the actual characterization is. We know that you need no more than weak to randomness. We aren't quite sure you could get it as weak as balanced randomness. We'd love to know. So this bit is very much work in progress. We're hoping to be able to have a more solid answer maybe by CCR 2013. So I think that rather than continue to hypothesize, I'd better just end here.
Could you explain a little more about balanced randomness? Why 2 to the n?
Oh, so let's see.
I mean,
So,
what's the
I mean,
motivation for that? It has such a
it's-
nice sounding name that
Yeah,
it
it's
should be
not.
a nice concept, but there seem to be some arbitrary things in the definition.
It's not my notion. I probably should be afraid to try to describe it. But no, I mean, so the idea is that just you can keep changing your mind about what the test is. So you know how for difference randomness you have a, okay, so do you know Demuth randomness?
Sort of,
Okay.
yeah.
Yeah,
Heard
okay.
it talk.
So the idea is that you're allowed to keep changing your mind about the about what each test component is. You're allowed to change your mind about V1, V2, V3. And for balanced randomness, you're allowed to chain a certain number of mind changes for each test component, and that change is going to be bounded by 2 to the n. So you can keep changing your mind more and more on
Yeah,
the...
it's sensitive to 2 to the n rather than 2 to the 2 to the n, or 2 times n.
Andre,
In the
perhaps?
paper, we actually worked this out. The 2 to the minus n is not important. It just matters is the inverse of the number of changes you allow. The measure bound should be the reciprocal of the number of changes. That's why it's called balanced. But you can replace 2 to the minus n by any sequence going computably to 0. Like 1 over n.
Oh, okay. I see what
Yeah,
you're saying.
and that paper is, let's see, who all, you and Selwyn and who else is it?
Hirschfeld, Miller, and E.
Yeah,
Some-
Andre gave a whole big talk on
Yeah, yeah.
balanced randomness. So we just,
Yeah.
I have another question. Well, you have you had something about Schnorr randomness, right?
Oh, yeah.
What is going on with Schnorr randomness?
Oh,
What,
that is a result by Gatch and Mathieu and Cristobal Rojas, basically saying that you can characterize the Schnorr randoms in terms of satisfaction of Birkhoff's ergodic theorem. You can say that a point is Schnorr random if and only if it satisfies the Birkhoff ergodic theorem, where the functions involved are simply the characteristic functions of effectively closed sets that have a computable measure.
what happens if you replace Birkhoff point by weak Birkhoff point?
In that theorem, well, okay, so if you would have to change the class of T that you were talking about. I mean, if you have, basically if you have an ergodic transformation, okay. I mean, if you have an ergodic map, then I think that if you have a weak Birkhoff, then you actually get Birkhoff. Yeah, I mean, if it converges, then it's going to converge to the right thing. That's the, difference between the two. So to talk about weak Birkhoff points, you'd have to, yeah, so if you were going to talk about weak Birkhoff points, you would want to say, well, suppose T is only measure preserving, and then see what happens. But if you're requiring that this particular T be ergodic, there's no difference.
Well, wait, it's ergodic. That just means, so from the fact that it's ergodic, you know that it will converge to the right thing.
Yeah.
If it converges,
Yeah.
but that's true almost everywhere. Does it, is it
It's true on
Yeah.
weak random points. That's random points. That
Yeah.
if there is convergence, it converges to the expected limit.
Oh,
Yeah.
okay. In other words, so it just if
And it's not particular to these theorems in general. Yeah.
okay. Very good. Thank you.
Just to understand, so originally the main theorem that you announced was about this was right after this. You said that
This one?
Martin, yeah, it's not Martinez, and there is a, yeah, and so then what? So I didn't understand then what. So you proved this theorem. Then which theorem is where you needed some condition?
No, this one doesn't. This one is the converse of the previous theorem by Nguyen, where that actually gives a full characterization here.
Yeah.
So this theorem here is of the form: if X is some sort of random, then under these conditions the limit exists. This theorem is of the same sort, yes? If this point is random of this sort, and you have a certain sort of function, then that limit exists.
So,
And the question we have here is whether or not this is optimal.
so just a minute. So previously it was about so the difference is that previously it was just about
closed sets, and right?
Yeah.
And here it is about arbitrary laws.
No,
Is
it's, that's here. It's not ergodic.
Yeah.
Well, in your first theorem, that was in your first
the
theorem, it was
original-
also not ergodic.
Yeah, that we were asking, all the results that Henry and I have
Yeah.
is for measure preserving T.
Measure
We aren't
preserving. So,
demanding
but
ergodicity.
that's why I don't. So the
Oh,
I'm
yes,
looking at the difference between that and this. So what,
Oh yes, I forgot to say T is measure preserving.
sorry? Yeah. So
Yeah.
but the difference between the first theorem and this.
Oh,
one.
here,
So it's
yeah,
worse,
here-
and there was and what was it?
it was computable.
Oh,
So
there it
here,
was
so
computable.
here we're requiring less of the functions.
Okay.
Yeah, and so if X is Martin-Löf random, it's not enough, or it's not known or what?
We don't know. I suspect that being Martin-Löf random is too weak a condition, simply because, well,
Actually, you prove that even
Yeah.
for F computable, it doesn't work.
no, for F computable, that's not so. So we know that weak to randomness works. We think that something in between the two might work as well. I kind of hope so, because it would be somehow a little bit disappointing to have gotten the optimal condition with such a strange proof. We don't have a reason that this should be optimal. Would be a lovely coincidence, though.
Martin-Löf is not enough, I'm sure,
Yeah.
because of the density.
Yeah. But
Yeah.
yeah, but perhaps balanced. But that seems like that would also take a great deal.
I know what I want. Another question. What if the F's are not computable or semi-computable, or just measurable functions like L1 computable or something like that?
It's pretty much the same. It works for layer-wise. Yeah.
Yeah. It could be,
Additional argument.
yeah.
Could you go back to your last slide again?
Yes.
So this condition, you said, essentially says that we can computably bound this integral only in terms of the norm and the epsilon that's given.
Yes. Yes. That's the condition.
That sounds a lot like some of these results from Ulrich Kohlenbach, where if you don't, but this is just speculation, but he claims that if you
That's
don't,
what this is. Yes.
if you don't touch separability in your proof, or if you don't really make use of the fact that your space is separable, you get really streamlined and uniform results that only depend on, say, the norm and something else in your space. This is something that looks like that.
All right.
So you may want to talk to him.
Yeah.
Presumably Henry knows him pretty well.
Yeah, but no, I haven't seen that reference. I'd like to.
Anyway,
Yeah.
Kohlenbach speculated about this to me. He said, but this looks like one of those, archetypical results almost, so you may want to talk to him.
All right. Okay.
Okay, so let's speak her again.